We have spent decades, centuries even, building an architecture of knowledge so elegant that we began to believe we had glimpsed the underlying code of reality itself. The Lambda CDM model, our standard model of cosmology, tells us that after the Big Bang, the universe began as a near-uniform soup of matter and energy. Over hundreds of millions of years, gravity slowly, painstakingly, assembled that primordial gas into the first stars. Those stars ignited, burned, died in supernova, and only then could their remnants collapse into the first galaxies. It was a patient process, a gradual one. The universe did not rush. Structure formed from the bottom up, from small to large, from simple to complex. A galaxy like our own Milky Way took billions of years to accumulate its mass, to gather its hundreds of billions of stars through countless mergers and feeding events. This is not speculation. This is the story written into the cosmic microwave background, into the distribution of galaxies we observe in our local universe, into the theoretical frameworks that have passed every test we have thrown at them for decades. And then there is the James Webb Space Telescope. In the months following its first deep field images, astronomers began to find something that does not fit inside our understanding of how the universe works. They found galaxies. Hundreds of them, scattered across the early universe, at distances so vast that their light has traveled for over 12 billion years to reach our instruments. These are not unusual in isolation. What is unusual is what they look like, how massive they are, and therefore how impossibly old they must be given their distance. The numbers are what keep astronomers awake at night. One of these galaxies, cataloged simply as JWST-ER1G, is a fully formed, settled disk galaxy at a redshift suggesting it existed when the universe was only about 300 million years old. 300 million years. To put that in perspective, the Earth had not yet formed. The Sun had not yet ignited. Our entire solar system was still chaos and accretion. And yet there, in the early universe, JWST-ER1G is already rotating with the calm, organized structure of a galaxy that has lived and breathed for eons. It contains stars that must have formed rapidly, in quantities that should be impossible for a universe this young. Another cluster, a collection of galaxies so densely packed and so luminous that they challenged brightness models, appeared at a distance corresponding to just 500 million years after the Big Bang. 500 million. The universe was still experiencing its first billion years, still cooling from the initial furnace of creation, and here is a crowd of galaxies acting as if they had been around the block a few times. The physics does not work. Let us walk through why, because this matters. Understanding the failure is the only way to understand the horror. The standard model says a galaxy of this size takes roughly 1 to 2 billion years to assemble from initial gas collapse to mature stellar population. That is a minimum, a floor, not a suggestion. You cannot simply conjure a fully formed disk galaxy in 300 million years from nothing. The math collapses. The simulations crash. When researchers feed the observed properties of these galaxies into models of structure formation, the models do not return a result. They return an error message. The universe is telling us that something is fundamentally wrong with how we think it works. The first explanation astronomers reached for was measurement error. Perhaps these galaxies are not as massive as they appear. Perhaps our distance estimates are wrong. Perhaps redshift calculations, which depend on assumed cosmological parameters, have led us astray. This was reasonable. Measurement error is the bread and butter of astrophysics. We are, after all, trying to calculate distances to objects 13 billion light-years away, using the trembling fingerprint of light that has been stretched and diluted across incomprehensible stretches of time and space. Mistakes happen, but the measurements have been checked, rechecked, analyzed by independent teams, confirmed with multiple instruments and techniques. The distances hold. The masses hold. The galaxy that looks impossibly ancient is impossibly ancient by every metric we know how to apply. The second explanation was observational bias. Perhaps these early galaxies are not actually unusual. Perhaps we are simply seeing a rare, statistical fluke. The extreme tail of a distribution we have only now begun to sample with Webb's unprecedented sensitivity. This, too, was reasonable. The early universe was messy. Extreme objects exist. Perhaps we have simply caught a handful of outliers and mistaken them for the norm. But as Webb kept observing, the number of these impossible galaxies kept growing. What began as a handful of anomalies became a catalog, then a collection, then a population. By the latest counts, researchers have identified over 300 galaxies in the early universe that violate mass, size, or formation timescale expectations. 300, not a statistical fluke, a pattern. And when you find a pattern where none should exist, you do not sigh and file it away. You begin to wonder what you have missed. The third explanation was that our models of the early universe are incomplete in ways we can fix with minor adjustments. Perhaps early star formation was more efficient than we thought. Perhaps supermassive black holes formed faster and powered extraordinary growth spurts. Perhaps there were exotic mechanisms, unusual merger rates, stealthy mechanisms we simply have not accounted for. Researchers ran simulations. They cranked up star formation efficiency to theoretical maximums. They seeded black holes earlier and larger. They introduced physics we had previously considered negligible. And the models still could not produce what Webb was seeing. The gap was not a small one. It was not a rounding error or a missing feedback loop. The simulated universes kept producing structures that were half the mass, a quarter of the mass, of what Webb was observing at the same redshift. The models were not failing slightly. They were failing completely. Something fundamental was missing, or something fundamental was wrong. At this point, the explanations begin to feel less like science and more like desperation. One hypothesis that has gained traction, quietly, in certain preprint papers and conference discussions, involves dark matter behaving differently in the early universe. Perhaps the dark matter halos that seed galaxy formation were more massive, more concentrated, or assembled faster than our standard models assume. If dark matter, which makes up roughly 85% of all matter in the universe, interacted with itself or with radiation in ways we do not yet understand during those first billion years, perhaps it could catalyze rapid structure formation that our current theories miss. This is not a crazy idea. Dark matter remains one of the deepest mysteries in physics. We have never detected it directly. We infer its existence from gravitational effects on ordinary matter, but its fundamental nature remains unknown. It is entirely plausible that our assumptions about how it behaves across cosmic time are incomplete, but even this does not fully close the gap. Even modified dark matter models struggle to produce galaxies of the observed mass so early. The anomaly persists. Another hypothesis involves modifications to gravity itself. Perhaps, in the extreme conditions of the early universe, general relativity operates differently than we assume. Perhaps there are additional dimensions, or extra forces, or quantum effects on cosmological scales that we have never detected because they only manifest in environments we have never had access to before. This is the fringe. This is the territory where respectable astrophysicists tread carefully, aware that they are approaching the edge of what can be called mainstream science. But Webb is not a respectable instrument. Webb is a truth teller, and the truth it is telling does not care about academic respectability. The most terrifying explanation, the one that circulates in whispered conversations and late-night papers that will not pass peer review for years, is that the universe we see in the early Webb data is not the universe our models describe because our models are built on assumptions that do not hold at all scales. Perhaps the universe underwent a period of inflation, a rapid expansion in the first fraction of a second after the Big Bang that left different regions with fundamentally different physical properties. Perhaps what we are seeing in the early universe is evidence that inflation did not produce a single, uniform cosmos, but rather an archipelago of pocket universes, each with its own constants, its own rules. If that is true, then the galaxies Webb sees are not impossible by the laws of physics. They are impossible by the laws of physics in our region of the universe. Somewhere, in an inflating sea beyond our cosmological horizon, different rules apply. And if that is true, then our entire framework, our standard model, our assumptions, our laws is not a description of how the universe works. It is a description of how one tiny corner of one tiny bubble in an infinite multiverse happens to work. We have been mistaking the local for the universal. We have been looking at one data point and calling it the truth. This is not a comfortable thought. But there is something worse. If the early universe contained structures that our physics cannot explain, and if no combination of known physics, modified physics, or dark matter adjustments can reconcile the observations with theory, then we are left with a question that is harder to ask than any of the others. We are left with the possibility that our observations of the early universe are not showing us a strange reality. They are showing us a false reality. That the light arriving from those distant galaxies is not painting an accurate picture of what exists out there. That something, somewhere, has misled the universe itself. Perhaps space-time is not what we think it is. Perhaps distance and time are not reliable maps. Perhaps the light from these galaxies has taken a different path, arrived through a different history, carried information from a region that is not truly where we believe it to be. The holographic principle, in its most unsettling interpretations, suggests that our entire three-dimensional experience may be a projection from a lower dimensional reality. If that is true, then perhaps the early universe is not actually early. Perhaps the light from those galaxies has been projected, distorted, or generated by processes we do not have the conceptual vocabulary to describe. We do not know. That is the whisper. That is the thing that must be said quietly, because saying it loudly feels like crossing a line we cannot uncross. We do not know why 300 galaxies in the early universe look like they have lived longer than time has existed. We do not know what physics is missing from our models, or what assumptions have led us astray, or what larger reality contains the universe we thought we understood. The James Webb Space Telescope has not found an anomaly. It has found a crack in the architecture of everything we thought we knew. And the crack goes all the way down. The universe has rules. We are no longer certain what they are.